This PowerPoint is covering control of breathing rate. We've done heart rates, now it's breathing rate. We'll look at how it's controlled, we'll look at lung volumes, how they can be measured, and then we'll look at spirometer trace and how you can use that to calculate lung volumes. So this links into CP17. So you looked at the lungs and when you, in A1, when you did about gas exchange. So hopefully you should be able to remember how we breathe in and breathe out, inhalation, exhalation. What I would like for you to do is pause the video and have a go, see if you can remember. Okay, so the thing to remember about inhalation and exhalation is ventilation is when you breathe in and you breathe out. You inhale and you exhale. Inhalation is an active process. It requires muscles to sort of contract. Exhalation is a passive process that happens as a result of inhalation almost. And it's all about changes in the lung volume. By changing the lung volume, you change the pressure in the lungs, and so that causes the movement of air. So inhalation, hopefully you've got this. You have the contraction of your external intercostal muscles. Remember, those intercostal muscles are the muscles between the ribs that cause the ribs to move up and out and increase your lung volume. And also your diaphragm, that big dome-shaped muscle that kind of sits under the lungs, that will contract and it will flatten down. So that flattens down and your ribs flit up and out. So you increase the volume of your lung, of your chest cavity basically. And so because you increase the volume, you decrease the pressure. So there's a change in the pressure volume from inside to outside, so air will rush in. Okay, you are contracting muscles. That requires respiration in terms of the muscle cells to occur. Thing to note, respiration and ventilation are two very, very different processes. Respiration is not breathing in and out. Respiration, hopefully you know by now, occurs in the mitochondria of cells to release basically stored energy in glucose. Ventilation is breathing in and out. So we've inhaled, so now we need to exhale, and it's kind of a passive process as a result of inhalation. And what happens is those bronchioles, where you have inhaled and they've taken sort of stretch because of the extra air coming in, they send impulses to the ventilation centre in the brain, sort of enough's enough sort of thing. So the muscles begin to relax, so your diaphragm will relax, your external intercostals will relax, and you'll get that elastic recoil back in the lungs. And I'm sure your teachers at A1 showed you lungs inflating and deflating when you did your pluck. Now, it mentions the internal intercostal muscles. Remember, they only really come into play during deep exhalation when you're breathing out quite forcefully, so when you force your air out, or perhaps if you've been exercising, so your breathing rate is quite deep and fast. Just normal breathing rate in and out, resting breathing rate, you won't be using those external intercostal muscles. So that's kind of what you know from the first year, as long as also to remind yourself about Fick's law. You might want to kind of bring that in here. We will talk about that in a minute. But that's kind of what you covered in A1. So adding on to it, A2, how is it controlled? Well, it's the brain again. And it's the medulla oblongata in the brain. It's the ventilation centre, handily named. And the ventilation centre, is receiving information from chemoreceptors that we met in control of heart rate. So there's those receptors that respond to changes in pH. So they respond to CO2 levels. But also the ventilation centre will be fed information from temperature receptors. So thermoreceptors, and also motor cortex feeds into that medulla oblongata. So when you start moving about and you start running or whatever you're doing, the fact that you are physically moving your limbs around will send information to the brain to let the brain know it's time to get the breathing rate up. Now, have a diagram on the handout. There is a handout that goes on with PowerPoint on VLE that you can annotate. And here you have this diagram here. So what we can see is, we'll start with this side first. So, changes in carbon dioxide, pH and temperature of the blood. Most likely because you're exercising is the usual reason why your breathing might increase. Maybe you're running the bus, maybe you're running upstairs, I don't know. Maybe you're, just running. So you're going to increase your rate of respiration because your muscle cells are contracting, so they need more energy. So therefore you're releasing CO2 as a waste. That CO2 is going to dissolve in the blood and form carbonic acid. It's an acid. It's going to affect the level of the pH of your blood. It's going to lower it. And then also remember temperature. Temperature is going to increase ever so slightly. Thermoregulation is going to occur to try and bring that temperature down. But you're making heat energy as a waste of respiration in those muscle cells. So the temperature is going to change. And that's detected by receptors. Okay, as it says there. So CO2 dissolves from carbonic acid, lowers your blood pH. Anyway, that is detected by receptors. So chemoreceptors in the medulla oblongata, in the brain itself, in the aorta and the carotid artery. So the same ones that are detecting, or going to send information about affecting heart rate will also affect breathing rate. Now, those impulses will be sent to the ventilation center in the medulla oblongata, and they will cause an increase in the rate and depth. So how many breaths you take per minute and the depth of the breath. You are, I'm sure, aware that when you have been exercising, you breathe faster, but not only that, but you also breathe deeper. I'm sure you've even seen people that have been, I don't know, running marathons or whatever they're doing, and you can almost physically see their chest moving up and down. And you can see sometimes their abdominal muscles come into play if they're breathing very hard. Now, this increase in rates, the number of breaths you take and the depth you take, enables you to maintain your concentration gradient. So it enables the removal of CO2 and the uptake of O2. Remember Fick's law. You need to know Fick's law, and if you don't know what I'm talking about, you need to revisit your A1 and learn about it. But you're looking at concentration gradients, you're looking at surface area, you're looking at thickness of the membrane. Okay, now, you will also have impulses from stretch receptors in the sort of lungs themselves, and impulses from sending impulses to the diaphragm, and all these will feed back into the medulla itself. And as I said to you earlier on, that motor cortex sends information about movement to the brain. So all these things will work together to control breathing rate. So as the rate of movement slows down, so impulses will be fed to the brain that the breathing rate can begin to return to normal, and it will do that once you've removed all the CO2 from the blood. So once that's the pH, as he's talking about here, pH has gone back to normal, breathing rate will return to normal. And those impulses will be sent down to the intercostal muscles and the diaphragm to lower the rate of contraction, so you breathe slower. Okay? So that's that. Now, lung volume, some key terms. I want to know what these mean, and you can, this is a bit of work for today, or part of it, you can put some definitions for me. I want tidal volume, I want breathing rate, I want vital capacity, and I want minute ventilation. I want the definition, units, and mean volume. So send them in. There'll be a link on the VLE for that. I'm undoubtedly going to tell you the answer to these questions as we go through this video anyway. So, moving on. They're the key terms that we'll be looking at. We'll be looking at tidal volume, breathing rate, vital capacity, and minute ventilation. And a way of measuring all these things is using a piece of equipment called a spirometer. Now, you have this diagram so you can annotate it. First things first is we have here a pen. Or you could link it up to a data logger like our Sparks ones that we use when we do the colorimetry. But you've got sort of pen here, and you can see it's going to produce a trace onto some paper there. Here we've got our tank, and in that tank will be air as a source of oxygen, so that'll be that tank there. And it's got this lid kind of floats, it kind of moves up and it moves down, and you can see that as it's floating up and down like that, it's going to move the pen up and down on the piece of paper. And it moves up and down depending on how much this person breathes in and they breathe out. You've got a counterweight here to stop it kind of flipping off completely. Soda lime, remember soda lime absorbs CO2, so you're just looking at the change in volumes there. We've got a nose clip and mouthpiece, so all the air coming in and out is going entirely through these tubes here, none escaping through the nose. And these are called the breathing tubes, and they connect up there. And they enable the different changes in volumes to be measured. And here we've got water on which that air bit floats up and it floats down. Okay. So how does it work? Well, the lid of the air tank goes up and down as you breathe in and out, and it makes a trace on the chart. You can set the speed, so you can sort of distance and time, so you can calculate rates. And they calibrate it by making marks on the chart with a pen before and after, sort of a known volume of oxygen is added to the air tank, and we'll see those dots in a minute. Now, basically, you count breathing rate by the number of breaths given in a given time. Breathing rate is generally how many breaths you take in a minute, BPMs. Very, very difficult to measure somebody's breathing rate, because as soon as you start measuring their breathing rate, people start altering it. So they either hold their breath, or they breathe quickly, they become conscious of the fact they're breathing. It's quite a tricky thing to do. And often if you're taking it in a clinical situation, they will do something else and not tell you that they're measuring your breathing rate. So they might be taking your pulse and doing your breathing rate, something like that. So tidal volume is the volume where they breathed in and out in kind of just a normal resting breath. So it's a tidal volume, how much you breathe in, breathe out. And it's the up and down movement of the trace. Now, you have this, so you can annotate this. So here, we've got our tidal volume. Bring it up. top there, bottom there, that's one tidal volume. And then we've got vital capacity, so we can see if that's from peak to trough. That is sort of how much air someone can exhale comfortably from their lungs. There will always be a bit of residual air left behind. And depending on the size of the person, it's sort of 5 litres. It does depend. Smaller people will have smaller lung volumes. Bigger people have larger ones. If you're a swimmer, you'll have better lung volumes. Or if you play like a wind instrument, I don't know, like a flute or something, they tend to have better lung volumes as well. Obviously, smokers will have reduced lung volumes. So lung volumes. And then there's a tidal volume. That's sort of a resting breath in and out. And you can see it changes. It's not sort of set. Some bigger than others, and it's not, it's not a tidy pattern there. And what we can see here is it tells us that time, 6 centimetres equals 1 minute. So each square is 1 centimetre. So 6 squares is 1 minute. So we've got 1, 2, 3, 4, 5. I'll do this first. So we're going to wear minute ventilation. A minute ventilation is your tidal volume times your breathing rate. Okay, so 1, 2, 3, 4, 5. Then I'm going to, because they've done a vital capacity there, 6. So that is 6 minutes there. Sorry, say that again. That is 1 minute there because it's 6 squares. Okay, each square is 1 centimetre. 6 centimetres is 1 minute. So 1 centimetre, 2, 3, 4, 5, and do a bit there, 6. So that's 6 centimetres. I said I haven't included that bit there because I've obviously measured vital capacity and then gone back. And I want to measure tidal volume. Okay, so I'm going to measure the number of breaths that you take in a minute. So the number of breaths here and then the number of breaths in this little bit here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, then 15, 16. Okay, so that's 16 breaths there. They're breathing and that's 16 times. And then you measure the distance. So there are various ways to do this. I'm going to show you how to do this again in a minute. But basically you pick a top of a peak and a bottom of a peak. And you kind of use the scale on this side to work out how much it is. It's not quite a litre. I made it 0.7. So I did 0.7 because that's the volume there. And the breathing rate is 16. So tidal volume is 0.7. And then I did 16 breaths. So you multiply them. 11.2 decameters cubed per minute. We're using decas because that's kind of what you do if we're using lung volumes. Now, something else you can measure is the rate of oxygen consumption between points A and B. So there's point A. Point A is there, and point B is there. Okay. So you work out what that is, and I worked that to be kind of half a decameter there. Okay, and that was in 20 seconds. If you kind of measure down here and measure down here, that was sort of 20 seconds. I probably should have drawn the line down to help you. But you kind of bring that line down to there, and you bring that line down to there, and that's 20 seconds there. And then that's half a litre in there. So you just do volume of oxygen divided by time. So it was 0.2 decameters divided by 20 seconds. So the rate of oxygen consumption was 0.025 per second. And that's how you work those two out. Okay, so Corprac 17. Corprac 17 asks you to use a spirometer to take various traces. Unfortunately, we couldn't, because of what happened this year, we couldn't do that. But what I've got is a trace for you, and I can show you all the things that you would have done, basically. We do have spirometers at college that we would have used, as do not look like that big thing. They're a handheld device that you link up to our data loggers. But you would have got a nice trace, hopefully, if you could stop laughing. So usually find students start laughing and become conscious, but we would have got something. Anyway, so this is what we're going to do instead. So we have a chart here, spirometer chart here, and it shows us 2 traces, one at rest and one at exercise. So you can see there's the person there, happily minding their own business, breathing in and out. And here's the one after exercise, so the upper trace. We've got the 3 dots here. Remember, these are the 3 calibration dots here. And we've got some details here of kind of what the graph, what it means, basically. Okay, so it shows you 3 dots above the upper trace are calibration dots. The bottom, so this one here, is the baseline level. So that's before anything's been added. The second dot is after adding 1 decameter. And the third dot is after adding another decameter. Okay, and they've told you that the recorder was set at a rate of 0.5 centimetre per second. Okay, so that's 0.5 centimetre per second. Now on the handout you've got a couple of these, so you can annotate them sort of as you wish. You can do a couple of things with it. So here, first things first, let's sort out what does it all mean. So, as I said, we've got after exercise here, and we've got before exercise here. Now, this bit here tells us 5 squares is 2.5 centimetres. Now, we know, because it told us in the stem, that between that dot and that dot, they added a decametre of air. Okay, so we know that 1 decametre is equal to 2.5 centimetres, because they told us in the stem. That means that one individual of those squares going up, vertically going up, you do 1 decametre divided by 2.5. So each one of those little squares going up represents 0.4 of a decametre. Okay, happy I did that? So there's 2.5 centimetres between their 5 squares. So 1 decametre we know is 2.5 centimetres because they told us in the stem that that gap there equals 1 decametre. So to get how much 1 square is, we do 1 decametre divided by 2.5 gives us 0.43. Okay, so over here, they told us in the stem that let me start again, sorry. They told us in the stem that the paper was passing through at a rate of 0.5 centimetre per second. So if it's 0.5 centimetre per second, 1 centimetre equals 2 seconds. Yeah, do you get that? Because it's 0.5 centimetre per second, so so 1 centimetre is going to equal 2 seconds. And again, same as going down, it's the same distance. So we can work, using this information here, we can work out the bottom here. So after 2 squares is 2 seconds, and if you count along up to there is 30 seconds. Okay, so that line represents 30 seconds there, that line represents 2 seconds there, and you can sit and work that out for yourself if you want, because I kind of, yeah. Okay, so first things first. So I put that up then just to remind us, and we've got our after exercise, we've got our before exercise again. Now let's work out mean tidal volume. Okay, now the best way to do your mean tidal volume is to get your ruler and basically do lines of best fit almost. So try and hit as many peaks as you can and as many troughs as you can. So put your ruler on and physically draw those lines so you cut across the sides where your graduations are so you can do measurings. There were 2 squares is 1 centimetre. So what we've done here, we've put them along there and we've counted that there are 2.2 centimetres there by working out counting the squares. And we know that each one of the squares is 0.4, so we do 2.2 times 0.4 gives 0.88, and it's literally a case of counting the squares. This is not a great scale, it's a bit annoying, but you know, you're not always going to get perfect scales in exam questions. Do the same thing down here, so we've put our ruler on and we've tried to hit as many peaks as we can, as many troughs as we can. We've brought it to the edge and we've counted 1.5 centimetres there, with 2 squares equaling 1 centimetre. So 1.5 centimetre there, so it's 1.4 times 0.4 because each 1 square, 0.56 decametres cubed. Okay, so that's how you do that. After exercise, before exercise, so oxygen consumption here. So start to finish. So what you do is we're going to do it in 30 seconds because we know roughly that line is, it's not perfect, but that line is roughly 30 seconds. So we put a ruler on, there's the start, okay, and there's the end. So we draw a straight line, and then we measure off here and we do the same thing here. Okay, 2 squares equals 1 centimetre. Oh, let me just put all the bits on. So here we've measured that as 2 squares, so that's 1 centimetre. So 1 times 0.4 gives us 0.4 decametre cubed. That's only in 30 seconds though, so we have to multiply it by 2 to give us 0.8 decametre cubed per minute. Remember, that's it, so we times it by 2. And then here, it's 1/2 centimetre, 0.5 centimetre, 0.5 times 0.4 gives 0.2, and you've got to multiply it by 2 to get it per minute, so it's 0.4 decametres per minute. Does that make sense? Hopefully it does. We'll find out in a minute. Because what I want you to do now is have a go at this exam question. And again, this is on the handouts, so you can use the handout. But basically, exercise has Exercise and effect on oxygen consumption, the efficiency of ventilation, the risk of type 2 diabetes. A spirometer can be used to study oxygen consumption. The spirometer trace shown was obtained for a 90 kilogram male at rest. Calculate the mean rate of oxygen consumption at rest for this person. Now, please look at the units. Centimetres cubed per kilogram per minute. You're going to want to be doing something with this, aren't you? Because it's per centimeter cubes per kilogram per minute. Yeah. So you're going to want to be doing something with that. So answer that question and send me your answers, please. Email them to me and I will pop on the answer to that, explain the answer to that at the start of the next video.